Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're excited to introduce to you the new TI-SensorLink Adapter. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight, I'm pleased to be joined by our two panelists, Stacy Thibodeau and Carl Haas. Stacy holds Bachelor's of Science in Biology and Chemistry, as well as a master's degree in Educational Leadership from the University of Louisiana at Lafayette. She currently teaches at Southside High School in Youngsville, Louisiana, where she teaches all levels of chemistry. She uses TI technology to assist her teaching, data collection, and modeling math concepts, linking them to science content. Stacy, thanks so much for being with us.
Thanks for having me, Mike.
And Carl is a graduate of the University of Heidelberg with master's degrees in physics and science education. After moving to Florida, he is now at the Pine School in Hobie Sound, Florida, where he teaches AP and honors level classes in physics and statistics. As a TQ regional instructor, Carl has presented at conferences around the nation, and he is especially proud of adding a newly designed STEM lab course to the Pine Schools program that integrates many STEM, hub, and rover activities. Carl, thanks so much for being with us tonight.
Hi, Michael. Thank you for having me.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Stacy or Carl using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We'll also be sending a link to the documents that are being used tonight by Carl and Stacy. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Stacy is going to discuss our agenda.
All right, so Mike kind of went over welcome and introductions. We are so excited to introduce you guys to the new TI-SensorLink Adapter that will go along with the Vernier sensors that you may have in your classrooms or at your schools. That can be used both with the TI-84 Plus CE and the TI-Nspire CX graphing calculators. And we'll show you some examples of some programs and projects that you can do with your students. And so these projects will expand on possibly what you're currently doing or maybe you want to do, either in your science or math classroom or STEM classrooms, and use them with the TI-Innovator Hub. And then at the end of the night, Mike will have a drawing for a summer registration for one of the workshops that will have lots of ideas for more coding and projects that you can bring in your classroom.
Thanks, Stacy. And Carl is going to discuss our expected outcomes.
Thanks, Mike. We're looking forward to explore with you how this new TI technology can strengthen students' understanding of sometimes hard-to-grasp scientific concepts. We will show you how to design some simulations for sensor-driven applications and how you can use the TI-Inspire CX or the TI-Innovator as a tool of inquiry. Now we'll introduce you to some simulations and activities that can help students discover connections to real-world applications.
Awesome. Thanks so much, Carl. Stacy, you have control. Feel free to share your screen.
Thanks, Mike. So when we talk STEM, the biggest thing is why do we do it, right? So it's the cool new thing to do in education. I teach chemistry, like Mike mentioned. I've been using TI technology to make concepts come alive, as well as doing some mathematical modeling. And so obviously the big S is important to me in my classroom, as well as the M, technology. I use the TI technology. The E by far is the most difficult one to pull in the classroom. But when somebody says, Stacy, why do you do STEM? This is why I do STEM. And this is why STEM is so important for us as educators for our future. I teach junior level students, sometimes sophomores, and I am getting students ready for jobs and careers that aren't even created yet. I pulled this that talks about or shows a graphic of where STEM jobs are going to be by 2022. When we look at it, it's not that far away. And the biggest thing for me was this 60% of the jobs will be in computing. And not necessarily that we'll need 60% of our workforce to be computer scientists, but have some computing skills that necessarily we can do in our classrooms. And so hopefully through the activities that Carl and I show you tonight, you can take activities that you currently do in your classroom and then STEMify them, STEM them up, where they're not just data collection only, but allows the students to explore some coding aspects, some engineering design aspects, and then kind of mesh the two together. So we'll see tonight that the new SensorLink is not just for data collection, right? So if you want raw data collection, we can still use the Nspire. We can use the 84 CEs. We can use the Vernier sensors to collect the data, to analyze the data. What information can we get from the data? Mathematical models of our data, plot our regressions, and so on. Tonight is, so what else can my kids do, right? So in my state, I live in Louisiana, and Louisiana adopted new science standards this past school year. We are not a true NGSS, which is the next generation science standards state. We've adopted something similar to it. And along with the new standards, there's a design component, and it's the freedom of a teacher now to be able to pull in design into the classroom to apply to the science and mathematics processes. And so that's what the SensorLink does. When this SensorLink first came out, I was so excited. I had a conversation with some of the TI people, and they were like, Stacy, why are you so excited? I said, this is the missing piece I've been needing. I've been so data-driven with my students in both biology, when I taught it, and in chemistry, that I felt the need to still have some component of data collection. Well, now this is my solution. In my chemistry classroom, my students have done several of these different activities with the SensorLinks. And the conversations that they have now is no longer just here's some one-dimensional, two-dimensional data collection. It's what happens based on this data collection. So Mike mentioned earlier that you're going to get the presentation. So I did put links in here that if you are new to data collection, either with Nspire or the 84, you can have the links. But at the same time, the iPad app, we can't connect the sensors, but there is data collection within some of the activities. And so if you're new to STEM, or you're new to coding or programming, where do you get started? I'm a chemistry teacher by trade. I went to school to be a chemistry teacher. I taught biology classes, AP Bio, Chem 2. How did I get involved in this? And this is exactly where I got started. So Mike just sent everyone a little poll to see where you are and your comfort level. So if you don't mind, what is your comfort level with coding using the TI basic language, which is the language we use for coding, either on the 84 or the Nspire? And if you can select A, B, or C based on you. This will give Carl and I an idea how to go tonight, and at the same time kind of be real with yourself. Again, I didn't go to school to be a programmer. I didn't go to school to work with programming languages, but obviously it's important for my students. So 10 minutes of code would be where I start. With 10 minutes of code, they are tried and true lessons, whether you're using the 84CE, you're using the Inspire CX, and or the Innovator Hub, which we'll show a little more tonight, walks you through. You can spend 10 minutes once a week learning how to program with your students. There's teacher notes, there's student activities, the sample programs are there for you. That is actually how I got started. If you want more about the Innovator Hub, so if you're new to the Innovator Hub, this is the whole world of engineering design and what do I do with a program once I write it. It's cool to write a program, but what can I do with it? This is the availability of having more freedom in your classroom to have the STEM concepts. And so 10 minutes of code is here. There are some activities that are science and engineering design, science through engineering design, that there's no extraneous material needed. The simulations are there for you to use. There's some Path to STEM projects, which we've have several webinars on them as well, which is more for an advanced program where you're using the Innovator Hub and your calculator and a breadboard component. There's the TI-Innovator Hub with the rover attachments that has math and science, and so kind of an on-ramp to robotics. And then really a lot of information about the hub. So that just gives you some information about the actual Innovator Hub that we're going to use tonight. And then TI actually has an entire STEM team. And so the STEM team is made up of several individuals who their job is to support people like you and I. What can they do to make our jobs easier, less cumbersome, to incorporate STEM projects into our classrooms? And so whether you're doing it after your AP exam or your whatever standardized test your state has, or you want to try one with a camp or a club after school, these are example lessons or just project ideas that you can do with your students to give you, as the expert in the classroom, ideas on how to implement more into your classroom. As you can see, lots and lots of different activities. And if you're really interested in how this works, you can actually contact the STEM team and they can send you the materials to use for a trial. If you work for a school district where you want to invite your school board members, or you have community supporters that may sponsor your school to get those materials in your classroom, this link down here to fill out information, they will actually send you the materials to use on a trial basis. And if you answer any emails that whenever you need, if they need to walk you through steps, just to give you that opportunity to feel not so scared when you're trying new activities in your classroom. When Carl and I were preparing for this tonight, we ran into a few snags with some of the coding. We emailed the STEM team right away, and within an hour I got an email from them how to fix everything. There are others within the community who do projects. These guys are there for you. If you have an idea for a project, or like I said, you run into a problem, that's what the STEM team's there for you. So just kind of in general, how do you put STEM in your classroom? This would be the way I would start. Like I mentioned, the 10 minutes of code is definitely the first place to go. And then once you're comfortable with the 10 minutes of code and you want to try some innovator stuff, I would contact the STEM team. Ask them, hey, can I check out some innovators? I want to do these projects with my kids. And then go from there. Call your PTC or PTO. Maybe call some people from the district level and get them to come in and see the kids doing it. they'll probably be able to find you some money. I'm going to let Carl kind of introduce you guys to what is the SensorLink and give you some more information about that.
Thanks, Stacy. So what is the TI-SensorLink? The SensorLink is, you're too fast for me. Can you go back one slide?
I'm sorry.
So now we're good. So as you can see, that SensorLink is an accessory to the Innovator Hub, an accessory that expands the capability of the hub, and it expands the possible projects you can do with the Innovator Hub and some of the sensors that you possibly have in your classroom. Currently, the SensorLink works with and is supported for 4 of those Vernier sensors: the stainless steel temperature probe, the pH sensor, dual range force sensor, and gas pressure sensor. And the STEM team, Stacy mentioned, they are working on providing some basic coding and some support for other sensors, sensors that may help us do some simulations and STEM projects. Now, there's a note right there. It says this is not a data collection solution. And interestingly enough, that sentence, that note is actually copied word for word from the TI website. So this is not a data collection solution. If you have sensors and you can connect them through USB directly to your computer, or mini USB to your Inspire, or through some interfaces to your computer, they still, an interface such as the lab cradle, that still remains a superior solution for pure data collection and data analysis. So the SensorLink is not a replacement for an interface that you use for data collection. So the question then is, what is the SensorLink? So if you want to bring up that next slide now, if it is not a data collection solution, then what does it do for us? What does it do for you and your students? How does it change? How does it enable us to change what we do, the kind of projects we do, and expand the usefulness of the Innovator Hub? And in the next 35 minutes or so, we will show you a couple of simulations that take that data collection to what we think is the next level of applications. So on that slide, you see the 4 currently supported Vernier analog sensor. And there's also a very small snippet of code right next to the pH sensor there on the right. So officially, those 4 are the sensors that are being supported. And I need to point out that Vernier actually has 2 gas pressure sensors out in the field, and one of them requires additional calibration, actually, that we will refer to again a little bit later. So depending on the model that you may have in your classroom, whether it's one of the newer gas pressure sensors from Vernier or not, there may be some additional calibration required. But those are the 4 officially supported sensors right now. So if you want to go to the next slide, Stacey. So a couple of notes before we get to our first simulation. If you want to use the SensorLink, it is required that you have the Sketch version 1.3 on your TI-Innovator Hub. And I'm going to let Stacy to kind of click over to on that link to show you where you would get that if you don't currently have that sketch on your hub. The SensorLink requires that you download and install TI-Innovator Hub software update, and the link that she's taking you to is showing you those 2 downloads. So it's a relatively straightforward process. You go to Software, OS Updates and Apps, look for the TI Innovator system, and you will find the Hub software update. update software that you need to download to your computer, and then you have the most recent sketch. This one as of, it's a little bit over a year old. So once you have that update installed, and once you have your sketch updated, you will have an accessory that works with a CE platform, CX, and the soon-to-be released CX2 as well. Some of the sketch commands for the TI-SensorLink are not yet in the Hub application. So if you download some of the software, the sample programs that we're providing tonight, you will probably begin to work on expanding them, changing them, modifying them, and what you'll find is that not all the commands are yet in the actual Hub app. So you may have to type words like Vernier yourself. But that's about the extent of what you need to do. And at the same time, you can, of course, use our sample programs and just copy and paste into the program editor. There's also an e-guide available to you when you get our presentation. You can simply click on that link as Stacy is demonstrating. It's great to have such a wonderful co-presenter. She's taking you to that e-guide, and you see right there are some of the code snippets. Again, they're just some very simple lines of code for the Inspire in those examples that would allow you to just read the data directly from that connected sensor. And so with that, I'm going to pass it back over to Stacy. We will talk about one of the programs. The first application, actually, using the stainless steel temperature probe called Some Like It Tepid, is actually an activity that is on the TI website already with support documentation, with teacher and student notes, and is available for both the CX and the CE operating system. So, Stacy, you want to take it back?
Yeah. So thanks, Carl. Appreciate that. So, like you said, Some Like It Tepid is available currently on the TI website. When I went to that STEM projects, it was there. It does have the code for the CE and the TI-Nspire. And so, temperature probe, sensor, link. So what we want to do first with it is learn how to use it with the actual software. So I'm just going to open up my software real quick. Just if you're new to coding in general, programming, TI makes it so that it's very user-friendly. We use basic programming language, and it's TI basic. It's very menu-driven, meaning everything you need for the program is in the menu. And so Carl mentioned that you have to have your software updated for the sketch updated for the hub. Your software also must be updated just to make sure. So when you go and you insert a page, if you do not see Add Program Editor, then your software needs to be updated. We had some new calculators at school. We got out of the box and pulled them out, and I was trying to show some of the students, and they were like, Miss Tibb, ours doesn't have that number 9. And so then I realized I forgot to update them. So if you're working with students and you notice that the number 9 Add Program Editor is not there, it's going to be a required update for your OS. So under Add Program Editor, we would say New, and then call this whatever. I'm just going to call it Temp. Depending on the type of program and if you want library access, I always say none. That way it doesn't go anywhere except on my handheld. And so what we have here, the program's name is temp. It's in bold. It's stored as a variable so that I can go find that variable on a calculator page later. It shows program and in program, and I tell my kids, just like when you make a sandwich, you want everything within the 2 pieces of bread. So your PRGM and your NPRGM are the 2 pieces of bread, and that's where you want everything in your sandwich. And so, like I said, everything's menu-driven. So when you're on the handheld, you actually go to menu, and everything is going to be done through Hub. And for this one, Carl mentioned it's not in the menu just yet for Vernier. And so I just tell my students we're going to go and connect an input, and I just pick one, and then I just backspace a little bit. And so I'm going to connect Vernier, and if I have one sensor, I'm going to say that I have one. I'm going to connect it to something. So I'm going to connect it to. That's what happens when you're working with the software. I'm going to connect it to, and we're going to show you a video in a second. Everything for the SensorLink goes in the N1 port. So I'm going to connect it to, and it's under ports, which makes sense. And I'm going to connect it to N1. So I'm connecting the Vernier sensor, which is connected to my SensorLink, to the N1 port, and I'm going to connect it as, and because this is the stainless steel temperature probe in this case, I'm going to do it as temperature. And then I'm done. So whatever I want now for the sensor to do, I've connected it. I try to tell the students it's kind of like when you have to connect your phone to the Bluetooth, right? In order for Bluetooth to work in your car or your AirPods, your earbuds, whatever, you have to connect it. And so we have to connect the input device into the hub in order to read it. And so initially, if I just want to read whatever the temperature is, maybe I just want to know, hey, what's the temperature? I can actually do that. And so if I go to Hub, I can send read. And again, for this one, I can't necessarily read it because it's Vernier, but I can read it as temperature. Like I said, everything is in the menu for you to actually find what you want to do. So it's really makes it so that programming, the language of the programming, you can walk through with students to be able to show them how to find everything. The 84 is the same. If you're on the 84 and you're interested in doing a new program, I want to create new. I'm going to call this temp. And I'm going to click enter. And I had temp already, and I connected brightness, but it can't be brightness. So I'm going to go to my hub menu. So I went to program and hub, and I remember it was an input because it's a sensor. And so I'm going to go to input. And then I tell my students I always just choose the DHT, which is a digital humidity and temperature sensor, just because it's easier to backspace out.
Shorter.
It's shorter, exactly. Just kind of one of those user-friendly things that you learn by doing. And I'm going to go to 9. And I'll do DHT. And then one thing you have to learn on the 84 is with the software, you don't ever just want to hit backspace because then it messes up the whole.
Takes out line.
It takes out the whole line. So I'm going to connect. I just did it again. Send connect input. I'm going to go DHT. I'm just going to delete the whole line. Sorry, guys. That's what happens when you're
when you're live.
I know.
We're live. All right.
Connect input. DHT. Backspace. And then you would have to physically type in the Vernier. So you get the gist of having to. So as soon as the update is available with TI, that the menus are available, obviously that'll be an announcement from them. So how can this be used more than just a data collection, right? So we don't want it to be, hey, just this is the temperature, but a lot of what we talk about if you are doing the new standards is feedback and then control, right? So those cross-cutting concepts of what happens if I do this, and we ask the students that all the time. So what happens if the temperature is this? And so I kind of showed you guys this, that we would connect the Vernier 1, because we have one Vernier sensor, to N1, that's the input import for it as temperature. We would read it and then get it. We could display anywhere. On the Nspire, we can display at a specific line item. We would tell it temperature is whatever is in quotes right here. It would display it at line 3. We would round that temperature, and then it would also put the degree Celsius. Now, this is the calibration that TI put together for this sensor, because most of us in science use degree Celsius. So let's do this. How can I use temperature data instead of just based on that experiment, but maybe I want to do some engineering design? And so we came up with the solution or the problem that sometimes when temperature is too hot for a specific machine, maybe you're working in some kind of engineering or industry, or maybe just your laptop computer. When temperature is too hot, I need to turn on a fan to cool it off. And so we have the availability to do that. So let's see. So I just have my stainless steel temperature sensor in a mug. My SensorLink is plugged in right here. It is connected to the input 1. This is how it's connected to N1. And then I have my Innovator Hub, who's connected to the Nspire CX2. If you haven't seen the CX2, here's the CX2 CAS version. And then over here to the right is where I have my servo motor or my fan plugged in. And so when doing this with students, they're like, hey, I did something. I built something based on the need, based on the data that was input. And so this was raw, obviously, not a huge engineering design, but it could be that the setup with cardboard boxes. Maybe you have some popsicle sticks. Maybe you have some Legos where you want the kids to actually design a fan that would cool off that temperature sensor.
So to add, before you go on, Stacy, if I may add something to it. In the beginning, we asked that question. So if it's not a pure data collection device, then what is it? How does it change or allow us to change what we do in the classroom? And this relatively simple simulation Stacy was just showing you is kind of illustrating that point, that she's not just reading, the sensor's not just reading the temperature, but now the code that we wrote prompts the Innovator Hub to do something in response to it. So there's an output that is based on the input that came from the data collection device.
Thank you, Carl.
Sure.
So this is, it looks very cumbersome. It's not a difficult program. So the way this program is set up, again, it has information in there for both you as the teacher, the user, but also the students. And so this symbol is nothing but a display that allows the user to know what's going to happen. It says this program uses data from a Vernier temperature sensor to turn on a fan, and this fan is called a servo motor. But I will display on the handheld that the SensorLink and temperature sensor and servo motor are all plugged in. And then I also put a little comment, hey, if you don't, when you want this program to finish, just press escape. And then when escape is pressed, the program will stop. So, Mike, can you do the next of the quick polls? And then we're going to see what do you think is going to happen in response to the temperature data based on this code that you see.
And we need more active participation on the quick poll than the last time. Come on now. You all click one of the three letters.
And Stacy and Carl, while people are thinking about that, we had a question from Robert. He asked if you can create your own sensors.
Yes. So with some of the breadboard components, you can actually design some of your own sensors. I will tell you that that is not my strong point as far as what I'm comfortable with my whole class of students. I have created a conductivity sensor. I've also created a temperature sensor using some of the breadboard components with students, but not necessarily, it's not with the component of the SensorLink. Carl?
I think that last sentence is important. If you want to use the SensorLink, of course, you would have to have a plug connected to your own design that then plugs into the SensorLink. Otherwise, you would have to connect it directly to the Innovator Hub. And I think the most difficult task is, of course, to calibrate your sensor so that the reading that you're getting is calibrated to some standard. Like the temperature sensor is calibrated to reading degrees Celsius. The gas pressure sensor is calibrated to output a reading in kilopascal. So if you want to use the SensorLink right now, the 4 Vernier sensors plus anything that you would design that has that analog plug that the Vernier sensors all have in common, that white plug.
Right. So if you're using the breadboard components, it's just numbers. It's picking up on levels of ions, let's say if you did conductivity, in whatever solution. It's not conductivity numbers like we would think of when we have a Vernier sensor, because that's ultimately what Vernier sensors are. They're picking up on certain levels of something, and somebody somewhere engineered it and designed it and calibrated it to read whatever. So yes, it is doable with some of the breadboard components, the extra links that are associated with it, extra conductivity probes and stuff. I actually have a project I'm working with some of my students in my STEM club where we're using the brightness sensor on the Innovator Hub itself, and they are 3D printing, which basically is a colorimeter box, and we're going to stick a little cuvette in it, a little test tube, and then shine a light on one side and see if we can get brightness data to actually compute and correlate to what the colorimeter from Vernier actually reads to be the solution data. That's my STEM club kids. They're a little more advanced than like my regular students I teach. But that's what we're doing. We're trying to design our own sensor. So that's a very good question.
I mean, if you're an expert in designing those kind of sensors, you probably know that many of them use potential difference, electric currents, or changes in electric currents as something is happening in the sensor, that then has to be converted and calibrated into some kind of a visual output, and that is usually the coding task that requires more expertise.
Any other questions?
How did we do any other? We have, right. So we have.
So with the chat, the majority of the people said that based on the temperature data, it's going to read, and then if the temperature is greater than 31, it'll set the servo on, and it'll display it a message that it's too hot. If the temperature is less than 31, it will say that it's just right. And that's exactly what this will do. And so if you have students that are interested in engineering, this is a true real-world example of what would happen if we didn't have feedback and control in our chemical plants, in our cars, in our computers, that if the temperature rises, sometimes we have to turn a fan on to cool off whatever is associated with it. So that is the code for the CX. And then as far as the CE, we have it displayed as the same, that we would display the temperature, set the servo 1, because we have 1 CW. In case you're new to servos, that just means that it's clockwise. It's at a speed for the servo motor to be at 50, and then it's going to run for 5 seconds. And we would also display that it's too hot. Otherwise, if the temperature is not greater than 31, they would say it's just right. If you are not a CE user or vice versa, notice at the CE you have to have the parentheses and the quotes. That's something big for the two of them. Earlier, when I was talking about plugging in, I mentioned that the SensorLink goes in input 1 because it's an input source. I didn't mention where I put the servo. So the servo motor actually requires an external battery because it's operating more than the electricity needed from the calculator itself. So we actually plug it into out 3, and the I/O input-output kits that you can buy actually come with external batteries. And so that's why it's in out 3, because it's actually a 5-volt port instead of just the 3.3 volts like the input and output 1 and 2 are. So that's a whole design part of the Innovator. Okay. Let's look at a different project. Any questions? I don't know. I hope we're not going too fast. It's availability of projects, and Carl and I just had a lot we wanted to show you guys. All right, Carl, you want to talk about the next project?
Pressure?
Yeah.
Yes. So the gas pressure sensor. What are some of the simulation one can think of? One that came to mind when we originally thought about is tire pressure. Many of our cars, all newer cars, probably have tire pressure sensors that indicate when the tire pressure in one or more of our tires is too low, and we get one of those little lights on our dashboard that indicates that. Other pressure monitoring systems that we can now simulate with this SensorLink and gas pressure sensor is, for example, gas pipeline. There are monitoring systems that are built in along the pipelines that will indicate if there's any sudden drop in pressure. And the program that we will show you, a very simple program, a very simple simulation, will simply assume that when the pressure in the pipeline drops to near atmospheric pressure, some response to it, again, the output, an audible, visible alarm will sound. So one of the things we have to establish in your program is what is that value of the atmospheric pressure, and then what happens when that pressure threshold is reached from an initially higher value. So if you want to take us to that example there. So Stacy has in her showing in her video again the Inspire version of it. Connected to the Inspire is the Innovator Hub now with the red light showing, and she has the gas pressure sensor attached, and you saw what happens as she, and you want to replay it, when she is increasing the pressure, when she's pushing on the syringe on the bottom there on the video, as she is increasing the pressure, it switches from red to green, so she's reached a pressure threshold that is considered safe. So on the next slide, you can see the first line in the program, end program box, is again connect Vernier 1 to in1 as pressure. So all you really have to change is in that line of code as pressure what sensor do you have attached to it. And then, without getting into too many details of the code there's the while in that line which is while key. While you're not pressing the escape key, the program will run. The program will read the pressure. So as soon as you want to stop the program from running on your Inspire, you hit the escape key. That is your stop button, so to speak. So you read the Vernier sensor, you get the pressure, and just like the sample we showed you earlier, you display in line 3 on the screen pressure equals, again, the value is rounded to 1 decimal place, and it's displayed in, it's calibrated to kilopascal. In that next line, you see if P is less than or equal to 105, and we just established to avoid regional differences in pressure, in atmospheric pressure, which is around 101 kilopascal. We put 105 as a threshold value. So once it reaches that 105 or drops below it, it will display in line 4, in the following line, the pressure is too low. So in line 3, we'll get a value of the pressure in kilopascal. In line 4, it will read pressure is too low. In addition to that, there is now output in response to that. It will do something. There's a line of code that says set the color to 255.00. For those of you who are fluent in reading RGB code, red, green, and blue, the red is set to 255, the highest value. The other two are off, meaning only red is on. The LED will be red. At the same time, it will play a sound, 512 hertz, for 5 seconds. So there are three responses that are based on the pressure value dropping below the value that we set as a threshold. You have the visual that's saying the pressure is too low. You have a color LED flickering going from green to red, and you also have sound, an alarm sounding. If the pressure is higher than some predetermined value, we set it to greater than 130 kilopascal, which is probably much lower than most gas pipelines or other pipelines are, but just as a sample value. Then in line 4, it will display just right, and you see the color output is 0, meaning the green value is at a max. That's what you saw. 255 is only green, the red is at 0, and the blue is at 0. And sound at 256 hertz for 5 seconds. Then to skip down, when we end the loop, end while we'll end this loop where it's reading and assessing whether it's too high or too low. The last thing the program there does, it sets the color to 0. In other words, the LED is off, and it sets the sound to 0 hertz, and it does that for 10 seconds. Not that you would hear anything during those 10 seconds because the frequency is at 0. So that's the example for a simulation of a gas pressure sensor, whether a tire sensor, gas pressure in a pipeline or oil pipeline, gas pipeline or oil pipeline, and other example I'm sure that you can think of. Then we have the TI-84CE version, which is again very similar, except in this case we have a slightly more simple version of a program. In this case, we're just connecting the Vernier sensor as pressure sensor. We're reading the Vernier sensor, we're getting the pressure, and we're simply displaying the pressure on the screen. And then at the end, we're simply putting a line of text on the screen that says the pressure test is done. I think at this point, I should point out that Vernier has 2 pressure sensors out there, and one of them needs a different level of calibration. So you will not get an accurate reading of about 105 kilopascal of atmospheric pressure at sea level. But for if you don't worry about the actual reading, about the actual value. The simulation will still work because you simply have to change your thresholds and just say, okay, if this sensor reads 115 as atmospheric pressure because it's not calibrated yet, that's going to be my lower threshold, and I'm going to set my higher threshold at a value above 140, 150, or whatever you choose. So you may have to play with that to find out which of the two pressure sensors that are currently out in the field you have. Stacy, you want to take it back and go to the next slide?
Yeah. So unfortunately,
we're kind
of running out of time. You know, like a teacher, you plan for more. So we also did 2 with the pH sensor, and I'll just go through them real quick. Mike did mention you guys are getting the files for all of this. And so what if we wanted something with a pool alarm? And so if the pH of the pool is not within the range of swimming, I need to know that that's not available. I want a visible and or maybe an audible alarm. So this one's a lot of programming, a lot of coding, but it takes into the same message that we did before. Read the Vernier sensor. You can, if the Vernier sensor is whatever parameter, then you do this. If it's not that parameter, go do something else, right? In this case, there's 3 if-then statements. And so if it's less, the pH is less than 6.8, it's acidic, you don't want to swim. If it's greater than 7.4, it's basic, you don't want to swim. But if it's in between, then it's ideal, and then the color of the RGB LED, like Carl was mentioning, is a different color. So really and truly just using data to drive some type of input or output. We did the same thing with the CE, if it's less than 7, we set a color. If it was greater than 7, we set a different color. And I have a quick little video showing it can be done on the CE.
There was never any doubt.
Yeah, I know. So it didn't make a noise because it was optimal pH. I know you're like, Stacy, really, you could have done a higher pH. But that's what I had on my home. We also thought that possibly, what if we did something with a digital litmus paper? And I thought this project part was really cool in that litmus paper is kind of boring, that you just put it in and it turns a different color. And what if you lose the container it was in and so on? So it will modify or program the hub's RGB LEDs to be a certain color based on the pH. And so this program is 2 slides long. So, Carl, we also spent some time with the force sensor. Same thing. If the force is too great or too little, then we turn a motor on. So, I hope you guys.
If I to just jump in for go back to the force sensor slide just for a second. This is one forward. This is where your creativity comes in, because you can really just add several lines of code there instead of just having one threshold value. If it's greater than this, then do this. If it's less than this, do nothing. You could, with a force sensor, for example, you can have it respond to different pressures as you pull or push on the force sensors. In this case, again, you have a servo motor that's being controlled by the amount of force that's exerted, and you could have different levels of force than doing something to run the motor at different speeds depending on the force that you apply. So you can go crazy there and just add some very simple lines of code just based on value being greater than or less than something, and have an output response to that. I think we have to soon pass it back to Michael, but you wanted to show the last 2 slides again?
No, just kind of reminding everyone that the STEM team is here for you. That if you have any questions, concerns, you want to see more about it, the STEM team is definitely there for you, and that's their email address again.
And our email addresses are on the presentation as well. So when you get that, you'll have our email addresses as well. Michael.
Thanks so much, guys. As we begin to wrap things up tonight, if you have any last-minute questions for Carl or Stacy, please try to get those asked. I know they'll do their best to get those questions answered. We mentioned a little bit earlier that there are some really great summer workshops that are coming to an area near you, and they could focus on lots of different things, but many things that might interest you, such as coding or things that are STEM-focused or STEM-specific. So please feel free to visit our website to learn more about the summer workshops that are going to be in your area and what they're going to focus on, and how you can register and learn more. Also, we're giving away to one lucky winner a free summer workshop registration, and tonight's lucky winner is Marianne Landers. So Marianne, congratulations. We hope to see you, as well as everyone else, at a T-Cubed summer workshop. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really hope you share your thoughts in the post-webinar survey. Feel free to continue the conversation tonight on any of the major social media outlets. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents from tonight. And I want to take a minute to actually show those documents. So Carl and Stacy did a really great job of organizing things. Carl or Stacy, Carl, do you want to maybe talk about how this is organized?
Yeah, we have, in addition to the PowerPoint presentation that Stacy shared throughout the session, we have two additional folders in there. One has all the SensorLink files for the TI-84. That's right there. And then two lines above that are the SensorLink files for the TI-Nspire. So depending on what your operating system of preference is, you can download that particular folder. We also added a small little document called Read This First. It has a couple of comments, a couple of hints or things to keep in mind as you get started.
Thanks so much, Carl. If you have any problems receiving those links for the certificate of the documents, hang tight. You'll automatically get a follow-up email in a couple days. And in that follow-up email will be a link to the recording, a link to the documents, and a link to the certificate as well. And if you're watching this on demand, please copy that link into your favorite browser to receive your certificate. So besides contacting the STEM team, which is probably, especially for tonight's webinar, probably a really good go-to, you can always give us a call at 1-800-TI-CARES or drop us an email at ti-cares@ti.com. Those will probably, if you have a STEM-specific question, will probably be directed to the STEM team anyway. So feel free to either give us a call, send us an email, or reach out to the STEM team. Thanks so much, Carl and Stacy, for everything you shared tonight. We're really excited about the new products. Thanks so much for sharing everything.
That was great. Thanks for having me.
And thanks so much to everyone for joining, and we hope to see you back online real soon. Have a great night.